All right, I've been kind of building up to this video, and I've been giving some ideas of how Smith charts work and how VNAs work and stuff like that, but I haven't really explained the Smith chart in the ultimate detail, and I don't see a lot of people talking about that, so I'm going to give it an attempt. This is not going to be an easy subject. There's going to be math involved. If you're not interested in this thing, fine. But this is an in-depth look at exactly how the Smith chart was done, what's the mathematics behind it, and maybe give you some ideas of what's inside of your VNA and what's going on. So this is an official Smith chart. You know, back in the way back days, there was no computers. You couldn't print these out on demand like I did this one. You actually had to buy a tablet of pages that had Smith charts drawn on them already, and they were usually printed like this. There's red curves and there's blue curves, and there's a scale down here that you use with dividers to measure things. So this is the way it was done in the way back days, and I'm sure a lot of people still do it this way. It's still a good way to figure out what's going on. But what really is at the core of the Smith chart? What is it trying to measure? Well, it's measuring impedance, and you're usually using it to make a good match. What does that mean to have a good match? Well, you have a transmitter and you have an antenna is one system. You maybe have two different things, but we'll talk about transmitters and antennas. And a match means that you have forward power that goes into the antenna, and if they're matched with impedance, then all of the power will go into the antenna. But if there's a mismatch at the antenna, if the antenna is not the same impedance as the transmitter, then you'll get a reflected amount of power that comes back. And so you have forward power and you have backward power or reflected power, right? And so this idea of that there's anything that comes back is bad, and there's a ratio here of goodness to badness, and we'll talk about ratios and different units. You may hear the terms VSWR, which is standing wave ratio. If you have a wave going this direction and then you have a wave going the opposite direction, they kind of interfere with one another and they set up a standing wave. And so the idea that there is some wave here, and you can actually measure that in a physics class with sliding slots and stuff, and it's complicated. But there is two waves, a forward wave and a return wave. And if you're going to measure the amount of reflected power, you generally measure it in volts. And so SWR is kind of a concept. VSWR is a measurement. A voltage standing wave ratio is a measurement of this amount of badness. You may also hear the term return loss, and it's, you know, you don't want any return loss. You don't want anything coming back, right? And so there's also a term that we're going to introduce today, which is called gamma, all right? And gamma is a Greek letter, and it's written like this, okay? It's kind of like a hangman playing hangman. It's the gallows. And gamma is just equal to a volts divided by a volt. So it's a voltage ratio, a lot like VSWR is a voltage ratio. Gamma is a voltage ratio. And this is the reflected voltage versus the what's called the incident voltage or the forward voltage, okay? So there's a forward voltage and there's a reverse voltage, an incident voltage, reverse voltage. And so the idea of this ratio is gamma. So ideally you do not want any return voltage. You want this to be 0 over something, right? And so a gamma of 0 is a perfect match. And if you have the worst condition, let's say you have a short, okay, and then you will have the same amount of voltage returned as the amount of voltage coming in. So you'll end up with V over V is equal to 1. Okay, so that's the worst case is 1. So the best case is 0, the worst case is 1. And There's also a concept of opens. An open also reflects the entire wave back, okay? And so a short can give you a 1, or an open can give you a 1. And how do you separate those two? Well, gamma is actually a complex number, okay? So unfortunately, we have complex numbers. So we have a gamma, we have a real part, and we have a imaginary part, okay? So imaginary. That's why I don't like to use this little I over here. I'm gonna make this an F, because this is forward voltage. You know, people get hung up on all of these letters and the right way to do it and the wrong way to do it, and don't get hung up on it. Understand the concepts, and then when you read papers and stuff, you'll understand what's going on. See, this guy was sloppy. He shouldn't have used a little I here, or should have been very clever that, you know, a little I here and a little I here mean completely different things, and so it gets complicated. But anyway, back to the point. We have gamma, which is actually a complex number. Why is it a complex number? Well, impedances are complex. We have a complex impedance at the transmitter, and we have a complex impedance at the antenna, and so we have this complexity here, right? All right. So what does this mean? It means that we can have a 0 when everything is matched correctly, but we could also have a +1, or we could have a -1, okay? So a -1 happens in the short condition. -1 is a short, and we'll figure that out later. And a +1 is an open, okay? And so, but it's always in the range of 0 to 1 or 0 to -1. It's always in that range, okay? So let's see if we can't make a graph to use this new thing we've just learned about, this gamma, okay? And so, let's see, I drew it. Where did it go? All right, so here is a plot of gamma, okay? We'll say this is gamma, okay, gamma. And here's 0. And here's +1, and here's -1. So those are all the values that gamma can be. It can be +1, it can be -1, right? But remember, gamma is a real part, and there's a gamma that's the imaginary part, okay? So we're going to have to extend this, okay? So we're going to have a, let's see here if I can extend this far enough. And here, I think that'll be good enough. Let's see here. Let's draw in the other coordinate, okay? And it can go to 1, and it can go to -1, okay? So you can have the real part of gamma, and you can have the imaginary part of gamma, and the maximum value is 1. Okay? And then you can have other things. You could have a point out here somewhere, right? And that point has a real component and it has an imaginary component. And it also has a length, which is amplitude, and it has an angle, right? It has some type of angle here and stuff. So you can do things with that. So what is this good for? Okay? Well, we're going to need some old tools. I have to go dust these off and get out my compass. Okay, so we're going to need a compass. And if we think about this, the idea that gamma can never be bigger than 1, it actually means that that is the maximum area that we, in our graphing, right? We can't graph outside that because gamma can never be bigger than 1, or the absolute value of gamma, the vector length, can never be greater than 1. So we're always going to plot in a circle, okay? So that's just an interesting fact. And what does this mean? Well, it means that here's the goodness, right? That center point is when everything is perfect. When you have, remember, gamma is volts over volts, and when it's 0, then everything is perfect, everything is matched. And anytime you move away from the center, you have a mismatch, okay? Well, what's a mismatch? Well, mismatch can be called return loss. It can be called VSWR. It can be called lots of things, and here we're calling it gamma, or the reflection coefficient, right? All right. So what does it mean to be goodness? Okay. So let's draw a couple other circles on here. All right. I'm going to draw some smaller circles. And I'm going to draw in a circle here. And I'm going to draw in a circle here, okay? So it's kind of like a target, right? You want to be in the center. And if you're not in the center, then you have a mismatch. And these curves here are actually, can be calculated. VSWR, maybe this one is 1.4, okay? And this one here is a VSWR of 2.0, okay? And so these circles actually equate to values of SWR. Now, you need to calculate them to plot them correctly here, and we'll get to that. But just be aware that's this new thing that we just have now. They can go from plus and minus 1, and goodness is in the center. And if you understand that there's complexity, there's complex numbers, which means that there's phase information, then you can have an SWR of 1.4 that can go all the way around the circle because the phase can change, right? The standing wave can move back and forth depending on the frequency, and you can move around in a circle due to these phase shifts and stuff. And so constant SWRs are on these circles, okay? So isn't this great? Why don't they use this instead of a Smith chart, right? It tells you everything you need to know. You can have these circles, and most of the time, people buy vector network analyzers. Well, today they do. They didn't in the past. But now that they're $50, okay, people are buying them and they're ignoring the phase information. They really don't care about the phase information. They really just care about the magnitude, which is the length of this vector. And really, it's this new Smith chart that kind of gets people freaked out. But if you had a system like this, you would just say, oh, well, just ignore the angle and make sure you're within the circle, okay? Then it would be easy to understand, all right? So, so this is the new concept. We have gamma. We have something called reflection coefficient. It goes from 0 to 1. And yeah, so let's go one step further. All right, we've introduced gamma, which is the reverse voltage divided by the forward voltage. Okay, this is a little f. Well, you can do some math, and you can figure out that what we're really wanting to measure is the impedance match, right? That if you have a perfect impedance match, then gamma goes to 0. So remember impedance. Impedance is actually usually, they use the letter Z to say impedance. And impedance, remember, there's a real part, which is a resistance, and there's a reactive part, that's usually X, and the little I or the little J, if you're in double E land, means that there's a complex impedance, okay? It's resistive and reactive, right? So resistors and inductors and capacitors, all right. Well, we can rewrite this as actually the impedance of the load minus the impedance of the transmitter divided by the impedance of the load plus the impedance. All right? And this is now going to be gamma, the real part, plus gamma, the imaginary part, times the letter J. Okay. All right. So this equation then says, okay, well, if Z0, if our target 0 is 50 ohms, okay, and then we want our load, our antenna, to be 50 ohms too, because then we have 50 minus 50, that's 0, right? Doesn't matter what's on the bottom, 50 minus 50 is 0. And let's say that we have ZL equal to 100, okay? Then we would have 100 minus 50, which is 50, divided by 100 plus 50. So we'd have 100 minus 50 divided by 100 plus 50, okay? So we would have 50 divided by 150, okay? Which is 1/3, okay? Or 0.33, okay? So we would say that gamma is 0.33. And remember, we have a circle. So we're about 1/3 of the way out, okay? About 1/3 of the way out on the circle. Okay. So you can see that maybe this is really nice because it tells us if we can measure the gamma, we can come back and we can calculate the impedance of the antenna. So again, that's going to be useful. All right, we're going to introduce another letter. This time it's going to be a lowercase z. And we're going to say this is the normalized impedance. What does that mean? Well, it means you have some load impedance, and you divide that by your input impedance or your target impedance, however you want to think of it, right? And you say that's our little z. That's not a 2, that's a little z. I don't know how I'm going to make big z's and little z's. I'm going to make them like this. All right, so if your impedances match, then your little z here is going to be 1, okay? And we can also say, okay, that's just like a resistor plus some reactance, okay? It's the same thing. And so we've introduced this new little variable, z, and we say that it's the resistive part you're interested in and the reactive part that you're interested in, because everything is complex, all right? All right, so if I haven't lost everybody already, I'm going to lose them now. So I'm going to link to a paper below that is very, very good, and it has all the equations you need. And I'm just going to, instead of writing it on the piece of paper here, I'm just going to show you some equations. It's not really, you don't really need to understand them. You just need to understand that they exist and there is a derivation for them, and it'll become clear when we start to actually graph things. So we've just introduced the concept of little z, all right? So we've already given you this equation. Gamma is complex, and it's also equal to this equation here. And now that we've introduced this new little z, we can substitute in little z. So now gamma is also little z minus 1 and little z plus 1, which is also r plus jx minus 1, because remember this is just little j, little z, I'm sorry. And so we have minus 1 plus 1. Okay, so now we have, this is the important part, okay? Now we have gamma as a function of r's and x's. Oh, this is not, it's not an F, it's a gamma, gamma. Okay, so gamma is a function of little r's and little x's, okay? So that's very, 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 very important, okay? So you need to understand that. So I'm gonna rewrite it here because I don't like it. Gamma is a function of resistance and reactance, okay? And that's the key thing we're trying to get here. Now there's going to be a bunch of equations, and it's basically going to say, okay, if we know gamma, we can calculate little r. That's equation 3. If we know little x, the reactance, here's the relationship with gamma, all right? And then the most important equations for Smith charts is this one, which is the real part of the gamma and the imaginary part of the gamma, and all as a function with little r, okay? And I know this is a bit of a hand wave, but trust me, this equation here, can you see that? I can't see the equation yet. Okay, so this equation here is the real part of gamma, and the imaginary part of gamma now as related to the reactance. So we have one set of equations that's little r, and one set of equations that's little x. So we have reactance, or resistance, the actual real part of resistance, and then we have reactance, okay? All right, so I'm going to show you this on a computer model that I put together, but we'll look at their graphs here first. And it says, okay, we're still plotting gamma, okay? We're still plotting gamma. Gamma goes from 0 to 1, 0 to -1, -1, +1. This is still gamma. But what we're going to do is we're going to take this equation number 5 that I just showed you, which is gamma as a function of little r, okay? And we're going to hold little r constant, okay? It's x here too. So let me explain this a little better. Okay, we have gamma as a function of resistance and reactance, okay? All right, so we're going to hold the first variable constant, and we're going to vary the second variable, right? So we're going to hold resistance constant, and then we're going to let reactance go anywhere it wants to go, and we're going to plot with the resulting gamma. And this is what we get. So when little r equals 1, we get this circle that goes through the 0, okay? When little r equals 2, we get this circle, okay? So we're holding r constant, and we're allowing reactance to vary, okay? And we get this. So we get a set of curves, and these are called r circles because we're holding r constant and we're letting reactance change, right? Well, what if we did the opposite? We have this new function, gamma, and we have it as a function of resistance and reactance. What if we hold reactance constant and vary the resistance, okay? What does that do? Well, you get these curves, okay? So this is for, like this curve here is for reactance equal to plus 2.0, and we let resistance change, and we get this curve here, okay? And here's reactance equal to -2, and we let resistance vary, and we get this curve. So we get these set of curves. It's starting to look familiar, huh? Okay, so there are ways to look at gamma in terms of whether it's in series or whether it's in parallel, okay? So if a circuit has some element in series and it's some resistance plus some reactance, okay? We could create an open. This value could get so big, this would look like an infinite resistor, right? We could allow it to be the best possible, and then we would get full amount of power through this thing, okay? So we could go from no power to full power, depending on its value. But if we had a system like this, okay, where, it's actually another line here, right? Where this is resistance plus reactance, then if this were open, if this were an infinite value, then we would get perfect transmission. But if this was 0, we would short it out. So in this case, we can make opens And in this case, we can make shorts, okay? So let's go back to the Smith chart. And we can see those curves that we just plotted in red, okay? The red ones go here, and then the red ones also go here. And those are all of the cases where we are in series. We can start at the center, and then we can go here to this point, which if you have a VNA, you know this is the open. When there's an open, you get to here, okay? So everything can go to an open. We can also plot everything reversed and plot them in blue, and you can see that everything converges on this point over here, which is the short, okay? So this is when things are in short to ground, right, from signal to ground. So you can get shorts here, you can get opens here, and so these set of curves, the red ones and the blue ones, all have names, okay? All right, so when you're using the Smith chart, you figure out whether you need to have a capacitor in series or a capacitor to ground, or inductor in series, or inductor to ground, and that's why there's two sets of curves. Now, your little VNA is not going to have both sets of curves on it, unfortunately. It really should. But a real Smith chart has both because you use both. Okay, so we've done little R circles, and we've done little X circles, okay? And then we're going to calculate some other things here, and we're going to create some things called G circles, which are those, and we can get to B circles, which are those, okay? So if you put them all together, you get that, which is the Smith chart, okay? And so the interesting thing that we've just done is we've shown you that the Smith chart is not actually plotted in the units you think, all right? In fact, if you go back to the Smith chart and you say, okay, let's plot some reactance, the math, there's no it's hard to plot on this, right? So actually, what this is an overlay of gamma. It's actually, you're plotting gamma, but you're putting a transparent overlay on top of it that put these other lines on there that allow you to read certain values and understand certain values. But the Smith chart is not actually plotting Smith values. It's plotting gamma values. So that's kind of the underbelly of a Smith chart. Let's go to a computer model that I've put together. It's not a model. It's just all of these equations in Matlab, and I'm using Octave. I'm using GNU Octave, which is a free program. So you could download this. I will put a link to my file and stuff if you want to play with this at home. And it will plot the Smith chart and hopefully give an idea what's going on. All right, I'm going to be showing you a program, and you can think of it as a Matlab program. I think it would run under Matlab. Matlab and Octave are pretty forwards and backwards compatible with one another, but I did write this in Octave, and Octave is free. You can download it. And yeah, so let's take a look at my little program here. And it's called Smith Save. I'll probably rename it when I put it up on the website. But it's gonna draw a Smith chart, okay? So what we're gonna do is we're going to normalize this to 50 ohms. So I'm gonna set Z0 at 50 ohms. I'm gonna have blue lines and red lines, and I'm gonna have some text and stuff. So we're going to draw some resistor curves, some resistance curves. And I have coarse curves that are heavy and fine curves that are fine and light in color. So the resistance curves are the ones that start on the infinity side and then travel across. Then there's conductance curves. Conductance curves travel from short and then go right, and they go across. They're just kind of a mirror image, okay? And then there are reactance curves. So that's the X curves. And they start at the open and bend upwards and downwards. And then there are subseptance curves, which are the mirror image on the other side. So let's go through these one by one. I can set breakpoints here. So let me plot the resistance curves. Let's turn this on here. So here you go. We've just plotted some resistance curves. We have infinity to 0, 50 ohms in the middle. So these are the curves, okay? And we're using those formulas in that paper. We are plotting gamma, which is just z minus z divided by z plus z. And then we're going to plot the real part and the imaginary part. So we're plotting the real part of gamma, and then we're plotting the imaginary part of gamma. And that's all you have to do. You're done. Okay? And then that does that. So then let's set the next breakpoint here after the conductance curves. All right. So those are the blue curves, right? They go the other way around. Okay, good. And let's do reactance curves. And those are the ones that bend up. You can see them bending up here. And looks like I have the colors a little bit wrong. I'll have to go back and see why some of these are red and some of them are blue. They should all be red. They should all be red. Red, red, reactance, blue, blue, reactance, they should all be red. So I'll change this to red. And I'll change this to red. Red, red. Okay, let's run that one again. And we have to start over. So go to here. And that's just the whole thing. So we need to set a breakpoint again. All right, so let's go back to the break curves. Let's get rid of all the breakpoints. All right, so let's do it again. Resistance, resistance, conductance, conductance. We can just do all of those. We'll set a breakpoint here. Okay, so we got the red curves and the blue curves. That looks good. And then the next thing we're going to plot are the reactance curves. So reactance, and let's run those. And there we go. So now the little lines that go up are all in red. There we go, going up, up, up. And then we will do susceptance curves, and they should all be blue, and we should then be done. Yeah, so these are all in blue. All right. So let's get rid of the breakpoint, and then let's run the whole thing. And, I still have a breakpoint somewhere. Oh, I have this breakpoint here. Gotta get rid of that one. All right. And there we go. We have a Smith chart. Okay. Official Smith chart. So that's the way you do the math. That's the way you plot it. And you end up with a pretty Smith chart with labels and everything. And yeah, there you go. So you remember my first graph here? I said, gee, wouldn't it be nice if it was such a simple thing? Just 0 to 1 and all the VSWRs were just circles and everything. Well, remember, this is still gamma gamma. This is the same thing. This holds true on an actual Smith chart as well. And so we can actually see that here on an official Smith chart. These things at the bottom here, okay? Now, Smith charts are always normalized to 1. They always have just 1 in the center. But you get to normalize it to anything. You can just call this 50. And then here's 50, and then this says 2.0 for the R curves. This is 2.0. So you just take 50 is 1. So 50 times 1 is 1. 50 times 2 is 100. So this is where 50 ohms is. This is where 100 ohms is. And then if you went up to 3, that would be where 150 ohms is. And it just gets bigger and bigger and bigger this way. And the other thing that's interesting is, remember, well, I can just draw it here, but if we have, we can just draw it on this one, okay? So the center point, instead of 1, we're going to call it 50 ohms. Here's a VSWR of 2, which means this point right here is 100 ohms. But it's also 2.0 over here. So what's 2.0? So 50 times 2 is 100. 50 divided by 2 is 25. And that's 25, okay? And then if we had a VSWR of, let's say, 5, okay, that'd be 5 times 50. That'd be out here somewhere. That'd be 250. Okay, so 5 times 50 is 250, but 5 divided by 50 is 10. So over here, it's 10. And so there would be a circle here that went between 250 and 10. So that's the funny scale here, is it goes from 0, a short, to infinity, an open, but it's symmetric about 0, and you could just multiply it out to get all the numbers. So that's the way the center numbers work. Now on an official Smith chart, let's go back to this one here, there's these scales at the bottom. Remember I said you could use those for certain things. So this one is labeled SWR. So we're going to put one point here at the center, and I'm going to put this exactly at 2, okay? That means that this is now set to an SWR of 2. So if I put it here in the center, and I draw a circle, okay, I've just drawn a VSWR of 2. So if you're inside the circle in your Smith chart, you have a SWR of 2 or less. Let's do 1.2. Okay, that's a really, really good one. So let's go here to 1.2. All right, 1.2 is right there. And we can then, draw a circle. And that is an SWR of 1.2. All right, we can label these 1.2, 2.0. All right, so that's what these things are done here. Now, if we wanted to have a particular, let's say, return loss, we wanted a return loss of 10 dB. All right, we would go here, and we would do a return loss of 10 dB, which is here, and then we get to draw a circle. So now we have a 10 dB one, and it's pretty close. It's pretty close to 2.0. And one of the holy grails is to hit a return loss of 20 dB. That's like super, super good. And so let's go here and set this to the number 20. It's right here on this bottom little thing here, and let's draw that circle here. And it's about the same size as the 1.2. So that's why they're used. Minus 20 dB is 1.2, and 10 dB is 2.0. So whether you grew up in ham radio land or you grew up in RF land, you use either return loss numbers or you use SWRs. It's up to you, but those things are down here. There's reflection coefficients and attenuations, all kinds of little things here at the bottom where you can draw things on your Smith chart. So that's pretty cool. I wish they actually would, my actual Smith chart on my VNA would love to have circles on it. That would be kind of a cool thing to do. Now, of course, you can just plot it scalar. You could have a graph of frequency versus VSWR, but it doesn't give any phase information, and so this has all the phase information. So how does your VNA get the phase information? If you remember, if I can remember where my first thing is here, remember? Gamma, which is the Smith chart, gamma is what we're plotting, is just volts over volts. So all the VNA has to measure is reverse voltage and forward voltage, and then boom, it's done. It just makes this division, and it's done. It's super, super trivial. Now, this is a vector voltage, though. It has both voltage and phase information in it. And this one has voltage and phase information. So you need what's called a vector voltmeter. So back in the old days, you could actually buy vector voltmeters. They were actually a big box, and you would measure the vector volts, and then you would do the math yourself, and then you could grab your piece of Smith chart, and then you could plot it on there yourself. But yeah, they were vector voltmeters, but the VNAs all do it for you now. So anyway, a long way around. I hope this kind of gives you an insight of what's actually in the Smith chart. It's actually a gamma positive gamma and imaginary gamma plotted in 2 dimensions, and then there's this overlay. There's these lines that are just kind of overlaid on top, and that's what the Smith chart is. And in case you do get around to reading the paper, it actually has these SWRs as well, and it shows you that if you have like a R equals 2, then your SWR is 2. And if you have an R of 3, then your SWR is 3. So it's the intersection of these R curves, and allows you just to do it, because it's just R over R, it's just V over V. Yeah, right? Remember, fundamentally it's V over V or Z over Z, and that's just impedance over impedance. So that's all these things are, is ratios.